We are finally tackling a very general computational problem, namely to find solution sets of linear systems of linear equations. So I've written down the general form of a system of linear equation, as we've seen in chapter 7 already. So here we've got the x1 to xn are the variables. We have this a11, a12, and so on as coefficients. And here we've got some numbers on the side. So these are all field elements, these a, I, j, and the bi. This is just the general form we have. The only additional bit of notation that I'm introducing is that I'm putting a brace around these equations. And this is just some additional notation that I haven't used in chapter 7. Usually if you have several equations and put a brace around them, then you will want to say something you're searching for a solution which satisfy all of the equations simultaneously. This is just if you want to indicate we really want all of the equations to hold. Put a brace around it and then the notation is clear. Okay, now this general system of linear equations I will call star. And whenever I refer to this star, I mean a system of linear equations which is in this general form. Okay, so this is what we've seen in chapter 7. Now, if we take a closer look, now that we know the language of matrices and have used the different formatism using matrices, we can also rewrite this in terms of matrices in a quite short way. Namely, first of all, the idea is that we want to write all the coefficients of these variables here into one big matrix. This matrix gets a name, definition 865. Consider the linear system star. The matrix that we get, I call capital A, which has the aij as entries. So the I is the row index, j is the column index, so precisely they are distributed precisely as in the system. So we would get the matrix if we would kind of remove all the x's here from these equations and so on. We only leave here the a's, then we would get the matrix very roughly. So this has m rows and columns, and the same does the matrix. So this is an m by n matrix with entries in k. This is called the coefficient matrix. Whoops, matrix of the system star. Oops. Okay, the coefficient matrix. Now, if you think about matrix multiplications and maps induced by matrices and so on, it turns out that this here is now the same as so we can write this in the same way by maps induced by this coefficient matrix. Namely, if we just write this as a vector here, these entries b1 to bm, so let's call it b. So b1 to bm, this as some element of k to the m. The system star is equivalent to just one equation that we can put. Namely, if we consider the matrix induced, the map induced by the coefficient matrix, just abstractly, and take a look at what the left-hand side looks like. So if we would take fa of x, where x is in his components x1 to xn. If we would write down this would precisely be the left-hand side of this equation, just as of this linear system, just as a tuple. So in each component we would have the ith sum here on the left-hand sides of these equations. So this system is equivalent to fa of x is equal to b, or we've introduced the short-term notation for this ax is equal to b. So this is a very concise way of writing such a linear system. Okay, so much for that. So denote the solution sets. And just to abbreviate a little bit of notation, so now I'm using the notation we used for solution sets in chapter 7. So this now, since the solutions of this system are solutions of this equation, and this was denoted by L, and then the linear map, Fa, comma, B. So this was the notation that we used for the solution set of this, and just to abbreviate this a little bit, I will just write L, A, B, so just this calligraphic L or whatever it's called, with index A, B instead of Fa, just to simplify things a bit. Okay, so what do we know about solution sets of these linear equations? First of all, by Theorem 730, if we have, and the idea was now that the solution set is, I've said this many times, never mentioned in lecture notes, an affine subspace. So basically if we want to know one solution and the solutions of the corresponding homogeneous equations, we know all solutions. More precisely, if we have some element which satisfies A x0 is equal to B for some x0, so just for some x0 in Kn, then we know that the solution space, the solution set LAB is the same as x0 plus LA0, which was shorthand notation for the sums of x0 with all elements of this. So this is the general form. So to find the solution set, this is now the approach we are going to take. We are going to find one particular solution and then take a look in general at the solutions of this homogeneous equation, because it turns out they are a bit more easy, a bit easier to determine, and we are really able to determine this explicitly in some sense. And we will derive a method of kind of how to do this, and later on see an example of how we can really use this to compute all the solution sets. But this is a crucial thing. Also, there's something easy to observe, namely if we have some invertible matrix. So so this is here important. Oops. If we have some invertible matrix T, that's GLMK, so an invertible M by M matrix, then we know that this equation is equivalent to, let me just squeeze this in here. So if we just multiply with T on both sides, this doesn't change the set of solutions, because we can multiply with T minus 1 then again, it's invertible, and get the same set of solutions. So this is really equivalent to TAX is equal to TB. So every solution of this equation is a solution of this equation and vice versa. So this means if we have such an invertible matrix, the solution set of LAB is the same as the solution set LTA TB. Okay, and this is the second crucial observation that we will need. So this means if we can find an invertible matrix which we can multiply the whole situation to get at some linear system which we can compute, then we're done, so then we know our solutions. And luckily, this is what we've done earlier in this chapter, namely when we consider the row echelon form. So far we've seen that we can, that was in the previous subsection, that we can always bring a system into this, always bring a matrix into row echelon form by multiplying with some elementary matrices. They were all invertible, so we have seen already that there is some invertible matrix with which we can multiply A so that the result is in row echelon form. Let me just write this down, because this is something which we don't need to prove, because this was already part of what we've seen so far. Just we haven't seen this explicitly, so let me just keep this written down as a fact. So let M and N be natural numbers. Then for each M by N matrix, A in M by N K, there exists an invertible M by M matrix, so there exists an S in GL K, such that, and now I'm using the formalism we did before, S minus 1 times A. It doesn't matter if I take S or S minus 1 here, because it's invertible, so, but I can always find an S such that this here is in row echelon form. Okay, now, the idea is now to use these previous observations and this fact to study linear systems where the coefficients are in row echelon form, and to study them in detail. And this is then, again, a form where we can use the special form of this row echelon type to really find solutions. Just to summarize, use these observations. Whoops. To study, in general, the existence of solutions of such a linear system, so of, in our shorthand form, AX is equal to B. Now, to existence of solution, the important thing is now, so if in general, if we have the equation which is, if we have a homogeneous equation, so B is equal to 0 everywhere, so if AX equal to 0, this always has a solution, namely the trivial solution always has the solution, so 0, 0, 0, 0, 0. Obviously, linear maps always map 0 to 0, so that's nothing to prove. But this, of course, is not a very, very interesting solution, but it has a solution. But the question is, but what happens if B is non-zero? So does this always have a solution? And in general, the answer is no. There are some linear systems which don't have any solutions at all. And now the first question is kind of what is the criterion? How can we decide if a system has a solution? And luckily this row echelon form really is very helpful in that sense. So we learned how to bring a matrix in row echelon form. So this is something we can do, or theoretically a computer could do. So we can just feed them with the Gaussian elimination method to bring something into row echelon form. So this is something we can do. There's a procedure for this. So this is good. Now, we can use this row echelon form, namely now in the following way. So again, let A be an m by n matrix, B be a point in K to the m, yeah, and let R denote the rank of the matrix. Okay, so it can be of arbitrary rank. So let now we apply this corollary directly. Let S be an invertible matrix such that S minus 1A, is in row echelon form. So this previous corollary just tells us that such a nest indeed exists. And now what we do is we put B prime to be the product S minus 1 times B, or the linear map induced by S minus 1 applied to B. So this is an m by m matrix, so the result is again in Km. And I want to call the entries, like this. Okay, B1 prime to Bm prime, the entries of the vector B prime. So this is something we can compute. We can explicitly bring everything in row echelon form, and then do the very same steps applied to the vector B and get a new vector B prime. So then the following statements are equivalent. Equivalent. 1, Ax equals B has a solution. And secondly, and this is now the criterion we need, the entries of Bi prime, if we consider now the idea, if we brought this in row echelon form, since the rank is some number R, we know that especially by the properties of the row echelon form, that in the rows below the rth row, everything is 0. So on the right-hand side of the equation, which is given by this vector B prime, everything else should be 0 as well. So if there's something, if there's a non-zero number, the equation, one of the equations in the system would be 0 is equal to something non-zero. So this is obviously doesn't make sense. So this should be necessary. But it turns out it's also sufficient because the only thing we need is that Bi prime is 0 for all I which are bigger than R. So the entries of Bi that are in a line where the row echelon form has a trivial, is trivial. The row is full of zeros in the row echelon form. Okay, let's prove this. Yeah, maybe that's already erased here at this point, because there's no point in doing one line of this lengthy proof. So yeah, let me erase. Okay, let's see. Let's start with a simple direction. So assume we have a solution of our system, and we want to show that then in the row echelon form, this holds for the coordinates of the right-hand side, the statement. So that's the easy part. First of all, this matrix, which is in row echelon form, a row equivalent to A, we denote this by B and denote its entries by Bij and define this as S minus 1A. Okay, now it was constructed in this way so that B is in row echelon form, which means, not this means, but it follows that Bij is bigger than 0 for all Bij which are in the rows below the rth row. So this means for all I bigger than R and all j between 1 and n. So that's a particular consequence of the row echelon form. Now, given that, so we have assumed that we have a solution. So a solution of Ax equal to B has a solution. Bx equal to B prime, which is just this equation here transformed by s to the minus 1. This has a solution as well. And this solution we just call x1 to xn. Now, for I bigger than rho, the equality of the ith rows in Bx equal to B prime is given as follows. So on the right hand side, let's switch sides here, is Bi prime, but on the other side we have Bi1 x1 plus Bi2 x2 plus and so on plus Bin xn. But since r is bigger than r, just by assumption, this is 0, and so on. This is 0. So the result must be 0. And this is what we wanted to show. So yeah, this is the easy part of the necessary condition. Now, let's assume the other direction. Assume we have this, that we have no contradiction in the row echelon form. So from that point of view, there's no obvious contradiction. So why does it follow that we already have a solution of our system? Now, for that point, we let J denote all the column indices of the pivots in the row echelon form. And it turns out that only these columns containing the pivots are really interesting, so to say. So this is a bit tedious to write down. So we call J1 to JR. So the rank is R. So we have R different pivots. And these are the column indices. So B, the column indices of the pivots of B. And we order them in the obvious way. We want that J1 is smaller than J2 and so on. Recall that there's a strict inequality between them, so we can just label them in the obvious way. Now, we do the following. We define a linear subspace of our general space k to the n. So the idea is now we are searching for a solution of our system x equal to b in a slightly smaller subspace, namely in the following space. Uj, capital J, is defined to be the space of all x1 to xn in Kn, such that xj is equal to 0 whenever j is not a column index of a pivot, so when j is not in capital J. Okay, this looks maybe a bit weird, and an easier way to write this probably is that this is the same as the span of the canonical base vectors in those coordinates. So we have only non-vanishing coordinates in these pivot coordinates. So this means this is the same as the span of the canonical base vectors ej1, ej2 to ejr. So here ei is the ith canonical basis vector. So just the standard notation we're always using. And of course, if we write in this form, we immediately see this is the linear subspace. And it's hopefully easy to see that this is exactly the same space. Now, let's maybe write this down. Uj is a linear subspace of Kn. And what we now want to do is to show something a bit stronger than we actually need to do. We want to show that the equation bx is equal to b prime, which is of course equivalent to ax equal to b, has a solution in this space, and it even has a unique solution in this space. This is more than we asked for, but this is a useful observation that we will need later on. Has a unique solution in uj. Okay, how can we see this? Now, we just have to think about what our system of linear equations, which is unfortunately not on the blackboard at the moment, but the equations there look like this here, so forget about the zeros, so this is the general form. Now, of course, if we are in uj, we know that all the entries of the vector which do not have such a column index of a pivot as column index, they are all vanishing. And so the equations, if we just restrict to some element out of there, it becomes much simpler. Namely, now simplify the notation. So instead of writing this as x1 to xn, we write this as x is the sum over all, from k equal to 1 to r, xk times ejk. So this is just a linear combination, some arbitrary element of uj. And this just means that this time we have relabeled the indices. Now in the jkth component of the vector is the number xk. Okay, just to keep this, to simplify the notation here. Now if this is of that form, then by assumption, if we take a look at the linear equation that we want, the last rows, the last m minus r rows of bx plus is equal to b prime, they only contain zeros by assumption, so this is now where we use the assumption 2. Also, they are trivially satisfied. So we don't need to bother for them. Now, then bx equal to b prime is the case if and only if b1 j1 and now times x1, and now we just have to look at the case how many summands are vanishing. So the only coefficients that remain are those where the column index coincides with the column index of one of the pivots. So this would be b1 j2 x2 and so on to b1 jr xr, and this must be equal to b1 prime. So in the next row we would have b2 j2 x2, and here we now need really the row echelon form. This is the pivot element here, so everything on the left hand side in the multiplication is vanishing. This is where we really have the row echelon form. So plus b2 jr xr is b2 prime, and so on. So in the last row, so in the rth row, there we have the pivot element br jr. xr is equal to br prime. So here, so it's kind of diagonally going down. So this is just by the property of the row echelon form, so or by the properties of the pivots. Okay, and now you can probably see where we're going. So this looks now like we did Gaussian elimination, and now we can undo everything to get the result for these numbers, because so just by the properties of the pivots, also we know that bi ji is non-zero. This is how pivots are defined. Or just by definition of pivots, this always holds. So since bi ji is non-zero for all I between 1 and r, we obtain. So first of all, we start with the last equation. Here we can directly see what xr is, needs to be. So xr is just br prime divided by br jr. This is just some number, but it's a unique number that we get. So we can then take the second last row, which I haven't written down. There we only have two coefficients, so let me just write this down. So if we just, we know that this is xr, and now we can insert this in the second to last row, so into br minus 1 J r minus 1 x r minus 1 plus B r minus 1 J r x r is equal to B prime r minus 1. And this is not just arithmetics, we just have to put, with this we can insert here. I don't want to do the whole computation because that's kind of quite pointless. And the important thing, we're now doing mathematics, we only want to see that there is a solution. So the computations we can leave to the engineers or to the computers or whatever. So insert this into here, so then we have some equation which has an x in there and a lot of b's, and so we just can compute x r minus 1 from this. So this to get x r minus 1, and then we can iterate, and we can take the next row here where we can insert the formulas for x r and x r minus 1, and in the end get a formula for x r minus 2, and then we can kind of unwind everything here to get results. So iterate to get unique formulas for x1 to xr. And this shows that there exists a unique element x, which is by construction in uj, with bx is equal to b prime. And this is, of course, equivalent to ax plus ax is equal to b. And this is all we wanted to show. So we wanted to show there exists some element which does this. Okay, now we have, this is a bit tedious and it's not, I think the whole proof is not that complicated actually. It's just a bit complicated to write everything down in detail. But anyway. Okay, so we've now seen, we have now a clear criterion. We can already say if I give you a linear system, then you can do the computations, theoretically, with the elementary row operations and so on, and tell me immediately, do we have a solution or do we have no solution? Now the question is, so assume we have a solution, how many solutions do we have? What are all the solutions? So how can we find them? And for this we now need kind of somewhat the homogeneous problem, as we shall see, and now I will give you a full theorem which tells you how to find all solutions of a given linear systems of equation, assuming we know that solutions exist. Let's see that after erasing. We are now going to discuss the general theorem about solution sets of linear equations and what they look like. We will see that we always have some construction method and to see how we can obtain these solutions in very general. This is maybe at first sight not that helpful for computations, but we will see an example later on afterwards. So how can we compute solutions of some system of linear equations using this method? How to do this? It's more, you shouldn't see this maybe as a big theoretical result, but more of like an algorithm of how to find these solutions and how to do computations within. So basically for this theorem that I'm going to do now, the proof is almost as important as the theorem itself because it shows kind of the method and the way we're going, but this gives us the theoretical guarantee of about the solution sets and about how we can study them. Okay, namely, in the following way. So in the general form, this is theorem 868. So we have a matrix. An m by n matrix in a general way. We say that R is by definition the rank of the matrix, which might be any number at this point. And we assume now that we have some b in k to the m, such that ax equal to b has a solution. Okay, so this is what we assume, and we've seen in the previous theorem how we can find out if this holds true or not. Okay, now let B be another m by n matrix. Which is in row echelon form. Echelon form. Row echelon form, and which is row equivalent to A. When I discussed about this row equivalence and about the row echelon forms, keep in mind this is not unique. So we can always, I had the example, you could multiply rows of this to get another matrix in row echelon form, which is equivalent, a row equivalent to the original matrix and so on. So this is not unique. So row equivalent to A. Now, we use basically the same notation as we did in the previous proof. So let J be the column indices of the pivots of M. So this is a subset of the set of column indices, which is 1 to n, be the column indices of the pivots of B. Okay, still the preliminaries, and now we need the same linear subspace that we needed in the proof of the previous theorem, and one subspace more. Namely, we have uj and vj, subsets of k to the n. And as before, we say uj is supposed to be, and now I'm doing the span description, so now I've just called this set A, J. I haven't named the elements of this J1 to Jr, so the general shorthand fashion is now this is the span of all Ej. So again, the jth canonical base vector. I'm not doing this, not writing this down this time, but this is just the canonical vector here, J in J. So we have all vectors which have only non-vanishing entries in those columns where the pivots are. And we now put Vj to be very similar, with the only exceptions. So we have a span of all Ej, but this time we take such that all J is not in J. So the rest. And it's easy to see Uj and Vj are complements of each other. So Kn is the direct sum of these two, which is almost trivial to see. But this is this is only non-zero where the pivot column indices are, and this is only non-zero where this is 0, and vice versa. So they are kind of, this is a kind of decomposition of Kn into a direct sum. Now, okay, this is only prerequisites. This is taking a lot of space, I'm just realizing. Then, now comes the interesting part. There exists some C in K to the N and a map G which goes from Vj to C plus Uj. So the set of all C plus V where V is in Uj, such that the solution set LAB is given by all the solutions of the following form. We have y plus g of y. So this is just some element in Kn, where we go over all y in this subspace Vj. So this is parametrized by Vj, so to say. So for each element of this, we get a solution of the system. Right? And so this tells us which Uj part we need for this solution. Okay, now this looks a bit complicated, and now let's go through the proof, and I hope this is, because the proof is quite constructive, maybe this is quite illuminating, and then we see the example, of course. So, first of all, we have this row equivalent matrix, which means we have some invertible matrix, S in GLMK, such that B is S to the minus 1 times A. And we again use the same notation. We put B prime to be S to the minus 1B. And now we can basically do all the computations with the row echelon form. Now, we've seen, so we know that, first of all, maybe let's write this down once. AX equal to B is equivalent to BX is equal to B prime. And now since since B is in row echelon form, this is easier to handle than the general setting. Now, we've seen that in order for this to have a solution, we need that the entries in all rows below the rth row are 0 in this vector. This was the previous theorem. And we've seen a bit more, namely this was this uniqueness part of the proof of the previous theorem. For this, we first consider basically all elements of K to the M, which have this property that everything behind, so from the R plus first row on is 0. So this means we need, let's do it like this, KRM. I define this as the set of all, I don't know, X is a bad notation at this point, maybe, no, B is also bad, let's say A1, A2, and so on to AR. And so the first R entries can be anything, and the rest is just 0. and this as elements of Km, where A1 to AR, so you can write this is an element of Kr. So we just take something non-vanishing with R components and fill up with zeros. So we've seen, so this is, yeah, this is, first of all, this is a linear subspace. It's maybe worth noting. This is the span of the first R canonical basis vectors. Linear subspace of Km. So what we've seen before was that in the proof of the previous theorem, there we had just, we've seen that if we have some element here, we have a solution of the system. But we've shown, so of the system, if B is chosen somewhere in this space. No, B prime, sorry. But we've seen for every such B prime, we could find a unique solution in this space Uj. That was part of the previous proof. So by the proof of theorem 867, now let's do this formally. If we take some element of this space Krm, so for all, let's call them Q in Krm, there exists a unique element, X in Uj, such that Bx is equal to Q. Right? This was the proof of the previous theorem. Okay, so we have a unique solution of this for each element, and this means, first of all, that if we consider the map B, and I call now map Bj, by restricting B, or basically the map induced by B, but I'm identifying this with the matrix itself, restricted to Uj. So we see for every element there's a unique solution, which means that this map here is bijective if we restrict domain and codomain. So we go from Uj to Krm. So this map, considered like this, is bijective, and since B is linear, the restriction is linear as well. So this is indeed an isomorphism. Right? So this is what we have. Now, yes, sorry. Okay, now, so about the solutions. We make now first one observation basically about the homogeneous equation, namely, if we take y to be some element of Vj, of the complement of that space. Now, if we have y arbitrary here, so since by the row echelon form of B, we know that if we take By, so we insert B into our map induced by B, this always has to be in Krm. Okay, this is clear because all the rows from the first, from the Aptos first one on are vanishing inside this matrix, so this always needs to hold true. Now, since this is an isomorphism, so since we have this property, this means there exists a unique, there exists a unique xy in Uj, so this is because Bj is an isomorphism. We have an xy in Uj such that the following holds: Bj xy is the same as By, and we just put a minus in front, and since this is a linear subspace, this doesn't matter, so this is well defined. So we always have such a unique xy such that this holds, and this we can rewrite as xy is equal, since this is an isomorphism, minus Bj to the minus 1. The minus is going in front because everything is linear, of B of y. So this is well defined. It looks strange, but it's well defined. Okay, we get some better chalk. Now, so this is the formula that we have here. So such an element exists, and it's of this form. Then, by definition, and this is now where the homogeneous equation kicks in. By definition of xy, so we have that if we apply b to xy plus y, so put the sum of these two into our linear system, basically. This is now, just by construction, this is the same as bj xy plus by, and obviously since this holds, this is 0. So this is indeed a solution of the linear equation. Sorry, of the homogeneous equation. Now this means for every y, we can find some xy, so y in the space vj, we can find the element of the complement, which is unique, such that the sum of those two is a solution of the homogeneous equation. Now, to formalize this, thus the map G, capital G I will call this, from Vj to the set of solutions of the homogeneous equation LB0, which is given as follows. G of y is simply y plus xy, and this xy is defined by this formula. So yeah, maybe let's write this explicitly. This is y minus bj minus 1 by. This here always gives us a solution of the homogeneous equation. And obviously this is linear because these maps are linear. So there's only a sum of linear maps, which is linear. So is well defined and linear. Okay, we want to show more. We want to discuss injectivity and surjectivity of this map. Namely, we want to first tackle the injectivity, and we know it's a linear map, so it's injective if and only if the kernel contains more than 0. So assume g of y is 0. Assume this is the case. Then this means that y would be the same as bj minus 1 by, but this here is just by definition, this is an element of vj, but this here, it's a pre-image of this bj map, this must be in uj. So this must be in the intersection, capital J. This must be in the intersection of these two spaces, but if you take a look at the definition, this is just 0. So this means if g of y is 0, then y is 0, and so by our previous theorem, let me see if, yeah, that was theorem 710b. This means that, okay, this is irrelevant now, G is injective. Okay, now what about surjectivity? Here we take use a little trick, namely, by construction, if we take a look at the dimension of the space Vj, it's still here, yes, so spanned by the canonical base vectors which are not a pivot. So the matrix has rank R, so we have precisely R pivot elements. So here we have R vectors, which means that here we have n minus R vectors. So the dimension of Vj is n minus R. Okay, but now take a look at this here, the solution set of the homogeneous equation. So we have seen that basically this follows from the dimension formula for linear maps. So the dimension of LB0, this means that, this is, maybe I need a bigger equation, sorry. The dimension of LB0, this is just formally the same as the dimension of the kernel of the map induced by B, so just by definition of the solution set. But this is now by this theorem the same as the dimension of the whole space minus the dimension of the image. So the whole space is Kn, and the dimension of the image, which is by definition simply the rank of Fb, and this is of course, so this is n, obviously, and this is the same as the rank of B. This is what we've seen. But since A has rank B, A has by assumption rank R, and B is row equivalent to A, this means this must have rank R also itself. So we've seen that G is injective, and we've seen that both domain and codomain have the same dimension. dimension of LB0. And this is where we see a map between, linear map between finite dimensional spaces of the same dimensions is injective if and only if it's surjective, if and only if it's an isomorphism. This was theorem 710. 710 part C. G is an isomorphism. So this is nice because this particularly means it's surjective. So all the solutions of the homogeneous equations are described by like this. So we need to take some y in this space Vj and just get, for each y we get a solution, and so this is how we get all the solutions of the homogeneous equation. Okay, now how to go from there and how we get now the general solutions there of the whole equation we will see in a bit.